My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all in our International Physics Webinar and a virtual conference on CERN. So I think you have already come to know that we have arranged the virtual conference in last month, and this is our second virtual conference on CERN. So I'd like to say thanks, Dr. Cristiano and CERN for selecting our university. And we have with us Virginia from CERN and Cristiano. So I'd like to welcome both. So welcome both of you, and a very good evening and good afternoon to your part. And welcome to our university. So thanks for selecting our university as your host institution for virtual conference. So the title of our today's virtual conference is "The Journey from the Infinitely Big to Infinite Small," and our speaker is Dr. Cristiano Alpigiani, and he's a postdoctoral researcher, Department of Physics, Washington University, USA, and also researcher at Atlas Experiment, CERN, Geneva, Switzerland. So I think he have already connected with us. So I'd like to welcome our speaker. So Cristiano, it's your time. You can start your session.
Okay, thank you very much for the presentation. So yeah, hello everybody. We want to, with this short presentation, we want to give you an idea of what we do at CERN, why we need a laboratory such as CERN. And so I'll start with just the format of the conference, this sort of virtual conference. So that will be around 45 minutes, more or less in total, the presentation. And then we'll also have time for questions at the end. But also feel free to ask questions also during the presentation. So we actually have two guides. So it's me that I'll give you the presentation, but it's also Virginia, that is another physicist. She is working in another experiment, and she will help with answering your questions. So I can also keep an eye on the chat box. So in case you have any question that is related to the slide I'm in, I can stop, I can provide you with more details, more explanation if something is not clear. But if something is not directly connected to the slide, something general, maybe Virginia can help me. And then we can also have another chat at the end. Okay. Okay, so I'll give you also a link at the end, the Indico page, where you can actually find a survey with this is a new format for us, also for CERN, because we have started this during the COVID pandemic, and we are trying to collect feedback, like about the content and about the conference in general. This is meant to be like a general introduction to CERN that is for a very wide audience. So we are not focusing on particle physics, on cosmology, and so on. So it's a very general introduction to CERN. Okay, so let's start. A few words about me. I can see what you posted, Virginia. Oh, private chat. Okay. I think, can you all see the?
Yeah, we can see.
Okay, it's fine.
Carry
okay,
on.
So yeah, so a few words about me. So I'm a particle physicist that is working in the Atlas experiment. Virginia is a particle physicist. She's working in the CMS experiment. The other experiment, the Atlas and CMS, are the two big experiments on the LHC that discovered the Higgs boson in 2012. I'm actually working for looking for physics beyond the standard model. In particular, I'm looking for what we call long-lived particles. So long-lived particles are particles that are produced by the collisions of protons inside the accelerator, and then they can travel across your detector and decay at a certain point. Okay, these are particles that the particle physicists, the theoretical physicists told us that are coming from the dark hidden sector. Okay, so what you see here is actually the picture of the Atlas control room. What you see here is the control room, and what you see here is a nice murales of the Atlas detector. And I'm also working for a new experiment, and this is an experiment that will be installed, if approved, on the surface above one of the 4 experiments that is on the LHC, and this will be used to study very long-lived particles. And this is a big experiment, 100 meter times 100 meter, and as an experiment that is placed on a surface, it can also be useful to study cosmic ray. Cosmic ray is a free source of particle that is coming from our galaxy or also surrounding galaxy. It's still not clear where they come from, the origin of the cosmic ray, how they are accelerated at the energy they reach when they reach the Earth. So it's very interesting to study also cosmic rays. Okay, so just a few words about CERN. So CERN is a French acronym, and it's basically in English is European Council for Nuclear Research. And the idea was, after the Second World War, to have like a completely European laboratory with the only aim to search for fundamental physics. So you know very well that during the Second World War, several physicists were used for example, in Los Alamos laboratory to develop the atomic bomb. Right? The idea was, after the Second World War, to have a completely European laboratory and with no absolutely military application. Okay, so only fundamental search. And that was the original idea of the first council that was held in 1953. After here, the council became an organization basically like the United Nations. And what you see here is a picture of the day when the work of the construction of the CERN site started. So this is the countryside of Geneva, where now you have all the laboratory, and this is really the beginning of the CERN site in 1954. So CERN is an international organization, basically like the United Nations. It has 23 member states. They are mostly European, but not only European. They are, but for example, there is also India. And all these 23 member states provide CERN with an annual budget. An annual budget that for the 2020 is equivalent to 1.2 billion of Swiss francs. That this is more or less equivalent to 1 cappuccino per European citizen per year. Then CERN can use all this money to pay, for example, the personnel, to pay the construction of new detector, new accelerator, but also to pay, for example, the electricity bill and so on. But there are not only 23 member states that are working with CERN. CERN is more a world collaboration. In fact, we have several also non-member states. Non-member states are, for example, like United States. United States do not provide directly money to CERN, but they indirectly finance CERN. Okay? All these countries around the world have several laboratories that are paid directly by the US government, for example, by the country government, and they have technicians, engineers, physicists, facility where they can develop a new detector, for example, and also build new detector. And then these pieces of detector are shipped directly to CERN. So they are not providing directly money to CERN, but they indirectly finance the research at CERN. So you see that it's a very, very word collaboration. The word is pretty well covered. There are around 20,000 people that are allowed to, that are working with on CERN. We have 2,600 members of staff. These are CERN personnel, so people that are directly paid by CERN. Then there are fellow students, and I also have a slide about the possibility for students. Then there are also 2,000 people from external company. These are, for example, contractor, external company that do like build refurbishment, road work, and these are several. For example, there are several contractors coming from the surrounding country like France, Italy, Switzerland, Germany, and so on. And then there is the vast majority of the person that are the users. The users are people that are maybe working for some university in the United States, in Australia, and so on. They do some teaching. So part of the year is also dedicated to do some teaching, but they also do some research. They may be working on the development of a new detector, or, for example, the data analysis. There are also many people that do data analysis. So they might spend part of the time also at CERN, but they might also be not physically present at CERN. So on average, the number of people that are present at CERN is around 20,000, it's around 8,000, 9,000 people. So it's a very small town, basically. CERN, we have different facility. We have a fire brigade, medical center, hotel to host also the people that are coming to CERN, the student, but also, for example, the technicians, physicists that are coming for a short period of time. So now I have a slide about more the physics. So why we need a laboratory like CERN? So there are many open questions that are still waiting, let's say, for an answer. So I try to summarize what are the hot topic of the moment. So certainly one of the hot topic is dark matter. So what is dark matter? Well, we still don't know exactly what it is, but why we call dark? Well, because this matter does not emit any light, does not emit any radio signal. So we cannot really see it with telescope or radio telescope. So, but we know that when we look at the universe, when we see a galaxy, what we see with the telescope, it's only 5% of the matter that made the universe. We have no idea about the 95% of the rest of matter plus energy. Okay. So why we know that the dark matter exists then? If we cannot see, that's why we call it dark. Then why we know that the dark matter exists? Well, because the dark matter does not emit light, does not emit a radio signal, but it has a mass. So like the sun and the earth are connected, so they interact by gravity, the same does the dark matter. So the dark matter has a mass, it generates gravity, so gravitational force, and so the dark matter changes the behavior of the galaxy, the dynamics of the galaxy. So probably one of the most famous proof of the existence of dark matter is the rotation curve of the galaxy. Like all the galaxies, like the Milky Way, are not static. Okay, they rotate. Now you can calculate what is the expected rotation speed versus the radius, versus the distance from the center. So you can ask an astronomer, and an astronomer just looking at the galaxy can give you an idea of the mass, of the total mass of the galaxy, and how this is distributed versus the radius. So you take this information, you take your formula, and then you compute the expected speed versus the radius. You put this on a graph, and the y-axis, consider that you have the speed. On the x-axis, you have the distance from the center. Well, you see that the speed increase versus the radius reach a maximum, and then when you go in the halo of the galaxy, the rotation speed of the galaxy go to, let's say, very small value, to 0. This is what you expect looking at the visible mass. But then you take a series of stars versus the radius, and you measure what is the real speed of the galaxy. And what you find is exactly this. So it's completely different with respect to what we expect from the visible mass. Actually, inside the galaxy, the two curves are not so different. That means that the mass that is inside the galaxy is more or less the one that we see. But when you look at the halo, when we don't see any stars, actually there is a lot of additional mass. This is where this 27% of dark matter is coming from the difference with respect to what we expect looking at the visible mass and what we see, actually, what we measure in real. So there is a lot of additional missing mass in the universe, and we still don't know exactly what it is. There are many theories that predict the existence of dark matter, but it's still not clear what it is exactly. Then another hot topic is the matter-antimatter asymmetry. So antimatter is different from dark matter. So dark matter is a totally new particle. Antimatter is, let's say, standard. It's also standard particle. So you have a proton. The proton has an antimatter that is called the antiproton. The electron has an anti-electron, and so on. When the antimatter was discovered, at the beginning, physicists thought that it was simply a specular copy of the matter with just an opposite charge. So proton has an antiproton that is exactly the same particle, but it has only, the only difference is it has an opposite charge. Okay, it's fine. Then it was discovered more than 60 years, around 60 years ago, that this is not true. So matter and antimatter behave in a different way. There is, in fact, an asymmetry. This asymmetry is very, very tiny, so the difference between matter and antimatter is very, very tiny, but it's still not clear why there is this asymmetry and what are the properties that are different between the matter and the antimatter. And this might be also very important to understand why in the universe we only have matter. There is some residual antimatter, but it's a very, very, very tiny fraction, okay? And at the beginning of the universe, you expect to have an equal amount of matter and antimatter produced. But then at a certain point, the antimatter disappeared. And it's still not clear why this antimatter disappeared from the universe. That's why it's very important to study this. The mass of the neutrinos. The neutrino, I'll mention the neutrino in a second. The neutrino are neutral particles that have they weakly interact with the matter. So they are very complicated to measure, and we still don't know what is the mass. We know they have a mass, but it's still not clear what is the mass of the neutrino. And then also the origin of the universe, so the first fraction of second right after the Big Bang. This is something that is still not clear. So let's start from what we know. So the matter, the standard matter, you know that is made of a proton, a neutron, plus electron. Okay. This table summarizes all the fundamental particles that we know. So there are two families of particles, what we call the quarks. There are 6 quarks, up, down, charm, strange, top, bottom, and 6 leptons, electron, muon, tau, and each one has an associated neutrino. Okay, 6 quarks and 6 leptons. But actually the universe that we see, it's only made of these 4 particles, because proton and neutrons are made of a combination of quark up and down, and then you have the electron. So basically, when you look at the stars and galaxy, you only see this kind of particles. The other particle can be produced in high energy collisions in the cosmic ray, in the accelerator, and so on, but they all have they are unstable particles, so they transform into stable particles like protons or electrons and so on. And then we have 4 fundamental forces in nature. There is a gravity that we know very well. There is the strong force. The strong force is a force that keeps together the quarks inside the protons and the neutrons. There is the electromagnetic force. Take 2 charge, like 2 protons. Protons have the same charge, so they repel. There is a repulsive force between the two. If you have opposite charge, there is an attractive force. This is the electrostatic electromagnetic force. And then there is the weak force that is responsible for some nuclear decay, for example. Each force has 1 or more mediators. What are the mediators? The mediators are the particle that here we call gauge bosons, that are the particle that transport sort of information about the force. Imagine that you have these 2 protons that they repel, okay? But the closer the protons are, the higher is the repulsive force between the 2. So there should be like a sort of communication between the 2 protons that tells the proton that they are closer and closer and closer, sort of. And in case of the electrostatic electromagnetic force, the mediator is the photons. So the photon is the mediator of the electrostatic electromagnetic force. The gluons are the mediators of the strong force. The glue that keep together the quarks inside the protons and neutrons. The W and Z bosons are the mediator of the weak force. The W and Z boson were discovered, for example, in 1983 at CERN. And then in principle also, the gravity should have a mediator that is called graviton. But the problem is that it's still not the gravity still doesn't fit the scheme of the standard model. That's why there is no gravity included in this scheme, because it's still not clear how the gravity behaves at particle level. So there is still no theory that can connect quantum mechanics describe the particle with the general relativity, the one that describes the behavior of the black hole at the center of the galaxy and so on. But in principle, if you have a gravitational force, you should also have a graviton, and there are searches at CERN to look for gravitons. Okay, to study new particles, we need accelerator and we need detectors. There are many detectors at CERN. There are what I call the four giants one, that are the four big detectors that are on the LHC. And what you see here is a picture of the CERN area. What you see here is the path of the LHC, that is 27 kilometers, that is around 100 meters underground. And there are four detectors, Atlas CMS, LHCb, and HELICE. Here there is the Geneva city, here the Geneva lake, and this is the Mont Blanc at the bottom of the pictures. But there are many more experiments at CERN, not only the one focusing on the search for dark matter, Higgs boson, and so on, but there are many experiments. For example, we have an experiment that studied the neutrinos, experiment that studied the matter-antimatter asymmetry. The AD is the antimatter accelerator, and is what we call the antimatter factory. Okay, this is the place where we produce antihydrogen, and we study the property of the antihydrogen. So there are several experiments that study, for example, the electronic structure of the antihydrogen. They do spectroscopy on the antihydrogen to understand if it's the same. There are experiments that study the effect of the gravity on the antihydrogen. Because again, we don't know what is the effect of the gravity. We know very well what is the effect of the gravity on the matter. We can clearly measure very well, but we don't know what is the effect of the gravity on the antimatter. We can assume it's the same, but from the theoretical point of view, we still don't know exactly. It might be different. We don't know. So there are many experiments that do this kind of studies. There are also experiments, CLOUD, that is an experiment that studies the interaction between the cosmic ray and the aerosol to study the effect of the particle on the cloud, for example. And there is also an experiment that is not even at CERN, that is AMS. AMS is an experiment that was developed, was installed, and it was the control room is at CERN, but is installed on the ISS, the International Space Station. And this is an experiment that is studying the cosmic ray to try to understand better, for example, the dark matter. Okay, but there are many more experiments that are present at CERN. If you go on a CERN website, you can find all the details about this kind of experiment. Okay, so but to run an experiment, you need an accelerator. You need a particle that you need a machine that produces new particles. Okay, so what is an accelerator? This is something that is very uncommon, let's say, for like macroscopic world, because in a macroscopic world, if you take two apples and you smash the two apples, you will not be able to get two bananas. Okay, to this you will take you will get these mesh apples. So this is what happens in an accelerator. In an accelerator, we accelerate particles like protons, and we smash this proton, and we get totally different particles. Okay, we collide protons that are made of quark up and down. We can produce Higgs boson, we can produce electron, muon, and so on. Completely different particle. And this is thanks to this formula, the equivalence between the energy and the mass. So Einstein told us that the energy is equivalent to the mass, and thanks to this formula, plus also quantum mechanics, we can use this proton like a sort of vector to accumulate energy and to produce completely new particle. That is something that is very uncommon for like a macroscopic world. So this is a schematic view of an accelerator, like the LHC, a circular accelerator. So there are two beams of protons one going in one direction and the other one going in the opposite direction, okay? There are two beams. They collide in 4 points where we have the experiment, and then the two protons collide and they create totally new particles. Now, there are three main components in a circular accelerator. There is the accelerating cavity, that is the system that really accelerates the particle. The principle is similar to the one of the sea surfer. Imagine the sea surfer and the sea wave. The sea wave arrives, a sea surfer rides the wave, and the same wave moves the surfer close to the beach. It's a similar principle, I say. Consider that the sea wave is an electromagnetic wave, and the surfer is our proton. So inside this accelerating cavity, there is an antenna that generates a radio wave. Okay? Then, when the proton crosses the region where there is the radio wave, the electromagnetic wave, like the surfer, the proton can sort of ride the wave. And so it's pushed, like the surfer is pushed in this direction, the particle is pushed in this direction, and so is accelerated. And the proton gets a kick, okay? And then the particle make a turn, when it passes again in the other accelerated cavity, another kick, and so on. So every time that the particle make a turn, is accelerated, 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 accelerated. But when you give a particle a kick, the particle goes straight, okay? But this is a circular accelerator, okay? So you need something that guide your particle inside the ring. And this is the purpose of the bending magnet. The bending magnet that are like the fridge magnet are dipole magnet, so magnet with two poles. And these bending magnets are used to bend the trajectory of the particle. Now, in electromagnetism, there is a force that is called Lorentz force, and the principle is simple. So when you take a charged particle, and a charged particle enter in a magnetic field, the magnetic field apply a force on this particle, generate a force that bend the trajectory of the particle. Okay, you see also represented here. You have a particle that enter, and when it's inside the magnetic field, the trajectory is bent. Okay, so inside the accelerator, you have not only four, but you have a series of these bending magnets, and each one bend a little bit the trajectory of the particle so that we can have our particle circulating on a circular trajectory. Then the third component is the focusing magnet. So this is a bending magnet with the two poles. A focusing magnet has 4 poles, 2 north and 2 south poles. A focusing magnet is a special magnet that works exactly like a focusing lens. Okay. Now imagine a focusing lens. When you have a ray of light that crosses the lens, the ray of light are bent and focused, concentrated in one point. Well, we want to do something similar also with a proton. Why the reason? What's the reason? Well, simply because inside the accelerator, we don't have a single proton going around. We have bunches of protons. Bunches that have a length of around 30 centimeters and a minimum width of around 20 microns. And they contain more than 100 billion of protons. So more than 100 billion particles with the same charge. So what happened to these protons? They repel. So if you inject the beam, bunches, with this small size, the protons start repelling, and so the size of the bunches start increase, up to the point where the proton hit the pipe where they circulate, and so you lose all the protons. So you need to keep this proton squeezed inside the bunches. And this is the purpose of the quadruple magnet. They're used to squeeze this particle. So these are the 3 main components of an accelerator. Okay. There are many accelerators at CERN, not only the LHC, because also we have many experiments. So there is an accelerator chain where everything starts from the LINAC, a linear accelerator, so the proton starts here. And after the LINAC, the proton enter in the booster. The booster is the first circular accelerator. These accelerators are very small, but also very, very old. For example, this is from the 1972. And here they reach already 80–90% the speed of light. After the booster, the proton enter in the proton synchrotron. Proton synchrotron is 628 meters and is the oldest accelerator that we have at CERN, 1959. Here they reach already 99.9% the speed of light. After the PS, they can be sent to different places, like, for example, the antimatter factory, or they can be sent to the superproton synchrotron, SPS, 7 kilometer. That is the one that was used to discover the W and Z boson in 1983. Otherwise, they can be sent to the LHC, where they are accelerated at 99.999999% the speed of light. And when they reach the maximum speed, they collide in the 4 point where we have the 4 experiment. If you want to see it, I'll upload the slide. There is also a video with the path of all these proton. I can also provide Pretam, I can also send you the slide so that you can share with the student. I can also update in the page. But if you want, I can also send you. I put in a common place so that you can download.
Okay.
Okay. So, but where do we take the protons? So we take the proton from the hydrogen gas. Okay. The hydrogen is the most abundant element that we have basically in the universe, and it's very simple. It's made of proton and electron. So if you remove the electron, you only have you get this plasma of protons. And this is really the device that we use. Is called duoplasmatron. We take hydrogen gas, we inject this hydrogen gas with a certain rate inside the duoplasmatron, and we get our beam of proton that then is injected here in the LINAC. This is focus a zoom on the bending magnet. If you Google LHC, you will probably get this kind of picture where you see the tunnel and this blue pipe. These blue pipes are the bending magnets, so the dipole magnet. And let me zoom a little bit here. So inside the LHC, we have 2 pipes because we have one beam circulating in one direction and the other one circulating in the opposite direction. Okay. Around each pipe, you see this sort of brown half moon around. These are the bending magnets. These are the dipole, north, south, south, north, that are the magnets that are used to bend the trajectory of the particle. Now, we don't use, like for the fridge, like a permanent magnet, but we use electromagnet. Now, what's the principle of the electromagnet? What is generating a magnetic field in an electromagnet is a current. If you take a simple current of electron, if you take a simple piece of cable, okay, you connect this to a power supply, copper cable. When the current flows inside the cable, the electron generates a magnetic field, okay? And the magnetic field is proportional to the current that passes inside. So the number of amps that pass inside your cable. Now, to generate a magnetic field that we need for the LHC, that is a magnetic field of more than 8 Tesla, we need a very, very, very powerful current. We need current of the order of 13,000 amps. Now, I don't know if you have an idea, just to give you a general idea, how many amps we have in our house. In our house, on average, we have like 13 or 14 amps. So basically, the current that we need in the accelerator is 10,000 times bigger than the one that we have in our house. Now, in our house, when you think of the cable, we have a relatively small cable, right? Now, what would happen if we take 13,000 amps and we let this 13,000 amp pass inside this small cable like the one that we have in our house? The cable will probably melt immediately because the copper is, yes, a good conductor. In fact, it's used for a cable, but it still has an electrical resistance. So when the current flows inside the cable, there is like a sort of friction that generates heat. And the friction, the heat, is proportional to the current. So with a small cable and 13,000 amps, you will really get basically a huge amount of heat that will melt immediately, vaporize the cable. If you want to use copper, and you want to use this very big current, you have to increase the size, the section of the cable. The problem is that if you want to use copper, the size of the cable will be very, very big, and we don't have only a single cable, but we have several cables, so you will end up with a magnet that is huge, that will certainly not fit inside the tunnel. So then how we can build a magnet like this? Well, we don't use a copper, but we use special material that are the superconductors. The superconductors are material, in this case is an alloy of niobium and titanium, that in certain conditions, they have zero electrical resistance. So with no electrical resistance, you don't have the problem that when the current flows inside the cable, you have a friction. You don't have any heat produced. So that means that you can use a small cable and a big current, because the electrical resistance of the cable is zero. This is how we can build a very small magnet using superconductor. And the problem of the superconductor is that they are not superconductor at room temperature. To have a material being superconductor, you need to cool down the material. And the temperature is minus 271 degrees. So the magnet of the LHC to work have to be kept at minus 271 degrees Celsius, precisely 1.9 Kelvin. So the accelerator is the LHC is a very powerful accelerator, but also a very powerful fridge. And we need to keep almost 27 kilometers at this very low temperature. So it's a big consumption of energy, in fact. Consider the consumption of the LHC is basically equivalent to the consumption of the center of Geneva. It's around 180 megawatts, and part of this is used to for the cooling system. It's around 40 megawatts. Okay, so let me come back to the Zoom, otherwise I will not move. Okay, so we have accelerated our particle at almost the speed of light. We collide the proton in the 4 point, and we produce completely new particle. So what we need a powerful camera to measure all these particles, to measure the property of the particles that are produced by the collision of these protons. What I have here is the ATLAS detector. And by the way, these ATLAS CMS are not very small machines, small device. They are very big. Consider that this is a person compared to the size of ATLAS. It's 44 meters times 22 meters for a weight of 7,000 tons. ATLAS is the biggest one. CMS, for example, is a little bit smaller, but for example, it's much heavier. It's 14,500 tons, so twice, double the weight of ATLAS. So this is a very, very huge machine, cathedral, let's say, underground. But if you understood what is the principle, how the ATLAS detector works, then you have understood also how the other detector like CMS, AMS, and so on works. So they will have a slightly different layout, different detector technology, but the principle is the same. So in a particle physics detector, you have to measure the property, the fundamental property of the particle. That is, you need to measure, for example, the trajectory of all these particles that are produced by the collisions. You have to measure the energy. You have to measure the charge. You have also to understand the different kind of particle. It was an electron, it was a muon, it was a photon, it was a proton, and so on. So we have different subdetectors to measure the different properties. Okay? Very close to the point where the proton collide, we have the tracking system. This is made of silicon detectors that are sensors similar to the sensor that we have in a camera, and they can precisely track the trajectory of all the particles produced by the collision of protons. Outside, we have the calorimeters, which is in green and orange. We have the calorimeter are the detectors that are used to measure the energy. How do they measure the energy? Well, they absorb the particle. They are made of very dense material like lead and iron, some of them. And by absorbing the particle, they can measure the energy. Well, actually, they absorb all particles produced by the collision of proton except for two. One is the neutrino, but the neutrino, I told you, is a very, very weakly interactive particle. It's very complicated to measure the neutrino. We don't want to do this directly in ATLAS. There are dedicated experiments also at CERN, but in Japan, in the US, in Italy, they do this kind of measurement. It's not the main purpose of ATLAS. The other particle is the muon. The muon, if you remember, is a particle that is similar to the electron, but it has a mass that is much bigger than the electron. So the electron is absorbed while the muon escapes. That's why we need another detector, that is the one in blue, that is the muon detector to measure the muon particle. So, tracking system to measure the trajectory, calorimeter to measure the energy, and muon detector to measure the muon particle. How do we measure the charge? Well, if you come back to the formula, the Lorentz force depends on the speed of the particle, on the magnetic field, but also on the charge. That means that if you have a magnetic field generated inside your detector, positive particles are bent in one direction, negative in the opposite direction. So the idea is simple. We generate a magnetic field. Actually, in Atlas, we have two different magnetic fields. A solenoid that surrounds the tracking system. Oh, how? I see a question in... Okay. I think there was a question from Virginia. So there is this solenoid that surrounds the tracking system and a toroid that is made of 8 of this coil. A toroid is a torus, so a sort of donuts that surround the calorimeter to generate the second magnetic field. Then, once you have reconstructed the trajectory of the particle, just looking in which side of the detector the particle is bent, you can understand if it was a positive or negative particle. So separate matter from antimatter. Oh, now I see what's the problem. So basically, we have comment posted. Okay, yes. Okay, we can take after the session. Okay, because I see there are comment posted there, and but the private chat. Okay, sorry. Okay, so I have also a slice of Atlas where you see the tracking system of Atlas, and this is where all the trajectory of the charged particle are measured. Then we have the calorimeter, electromagnetic calorimeter, measure the energy of electrons and photons, and the hadronic calorimeter that measure the energy of the hadrons. The hadrons are all the particles made of quarks, proton, neutron, and so on. Then you see the muons measured by the tracking system, is not absorbed by the calorimeter, and then is measured by the muon spectrometer. Now, we collide protons, we produce particles, but that means also we produce a lot of data in terms of data side. We collide, imagine that we collide particles every 25 nanoseconds. So we have 40 millions of bunches of protons that collide per second. That means a huge amount of data. This huge amount of data need to be processed and need to be analyzed. So you can really do it with a few computers. You need a very powerful infrastructure. And this is the LHC computing grid. This is a sort of cloud that connects CERN, that is the core, with all the institute and universities that are working with CERN. This university have a small data center, so they share computers, they share CPU, computer where we can save it. We have disks, so you can save data, but you can also use the CPU to analyze and process all the data. So we have 1 million of computer core, CPU core, connected to this cloud. And this is our supercomputer that we use to analyze and process all the data that are coming from the LHC. If we sum up, just to give you an idea, the amount of data that we produce per year when the LHC is running, summing up the 4 experiments, is around 100 petabytes of data. 100 petabytes of data produced per year by the 4 experiments that is on the LHC. You can imagine that we need a lot of space. But CERN is not only fundamental search, because you might imagine there are many applications that we can use. I mean, imagine from the point of view of the detector, point of view of the accelerator, they might have many applications we can use for, like, say, normal life. There is actually a department that is called knowledge transfer that has the purpose of really make a sort of link, connection between the CERN and the external company, industry, several applications, aerospace application, medical application. For example, here, medical imaging, we can improve the medical imaging. This is an example of the hadron therapy. Hadron therapy is the treat of the cancer using a beam of protons. So this is much more efficient than radiotherapy. So radiotherapy can kill the cancer, exactly like hadron therapy, but it also has a drawback that it destroys part of the surrounding healthy cell. While with the hadron therapy, you can focus more on the area, so kill the cell affected by the cancer, damaging less the surrounding healthy cell. The web was born at CERN simply because we wanted to try to find a way of smart exchanging data, for example, and then that was the web. Also humanitarian mission. There is this project that is called UNOSAT. UNOSAT is a United Nations project where you can rapidly mapping the Earth surface, and we can use, for example, software, technology we develop at CERN to do this. And this is very important, for example, when there is some problem like a earthquake, some disaster, And this might help to rapidly map in the area and understand what are the areas that are more affected by, for example, the earthquake and so on. And recently also about against the COVID. So you have also production, for example, of sanitizer, ventilator, mask, and also use of a lot of data. There were several projects that they need a lot of computing power to do study on the data, analyze the virus, how this evolved, to try to find, for example, a vaccine and so on. So I have a slide just for student about the opportunity for student, since there are many kind of opportunity. You can go on a CERN website. There is a career.cern where you can find all the open position, like for technicians, engineers, physicists. Everything is public. So if you can apply, your CV fit the requirement, then you can apply, certainly. And there is also a subsection there reserved for student, and you see there are many program for the students. So if you're interested, just go on the website and you can find a lot of information. So thank you again. I have the last slide with also some additional link that might be useful, interesting, and also in any case you can go on the CERN website and you can find a lot of information there. Okay, so thanks a lot for being connected. So okay, then how do we want to, because I thought it was possible, yeah, okay, to post a comment here. Shall I go through them? I don't see probably many questions. I mean, if I look at the comment chat. So, well, I see only one question about the booster. So the principle is the same, okay? The booster has a similar principle of the LHC, okay? Also the proton synchrotron is similar. So all these accelerators have, they are not only used to accelerate, okay? Because, for example, the bunches I was talking about before in the LHC, these bunches are made, for example, in the proton synchrotron. And how we do it? With the resonant cavities. So using electromagnetic wave, we can manipulate, let's say, our beams. So we can create the bunches, we can stretch, squeeze this bunch on a longitudinal direction, and we can also accelerate. So this is true for the LHC, but it's also true for the SPS, for the proton synchrotron, and for the booster. Of course, the resonant cavity that are in the LHC are different from the one of the booster, and so on. But it's exactly the same principle. So we accelerate in the booster like in the LHC. As we are processing so much data, if a new particle is produced, then how can be identified? Well, in fact, this is one of the problem. I mean, we have a lot of data that are produced. We have some guidance from theoretical physicists, so we know how new particles should behave in a certain way. Maybe they have some special behavior, they have a special mass, they are produced in a certain way. So we have some guidance from theoretical physicists, but it might be also that some new particles are missed from our detectors, because maybe simply we were not looking for this kind of particle, maybe because there are, let's say, covered by other process, and maybe this is something that is we were not looking exactly for that particle, so it might be missed. So it's not simple. I mean, for example, for the Higgs boson, we know that we were looking for a particle that was decayed, for example, into electrons, into muons, and so on. But we were not sure, we didn't know before discovering it what was the mass, for example. So we were doing different hypotheses. Okay, is the mass this? No. Is the mass this? No. The mass, and so on. So we do a lot of statistical analysis, and with also some guidance from the theoretical physicists, just to focus on particular part. But yeah, we also try to be open-minded. So I don't know if I answer. is CERN trying to create black hole, quantum black hole? The answer is yes, but this is, as you said, is a quantum black hole. We haven't seen any quantum black hole, but there are many theories that say that when you collide protons at a certain energy, you should be able to create a quantum black hole. Now, the quantum black hole are different from the macroscopic black hole that are at the center of the galaxy. So they basically behave from our point of view like particles. So imagine that you have this proton that collide, this create micro black hole that how they evaporate with Hawking radiation. So basically they transform into particles. So we are looking for some particles that are behaving in a weird way that might maybe come from a decay of the black hole. As far as I know, I don't know from CMS, but as far as I know from atoms, we haven't seen any quantum black hole at the moment yet.
Thank you. We have another question. So please can you say to apply in CERN for research or career, what qualification needs for a MS in physics?
Well, I mean, it depends on what on the application. To be honest, I don't know. I mean, I don't know the details. But if you go on when you get the slide, if you go here, career.cern, you will see the open position. So it depends on the level. I mean, if you apply for summer students, then you need to apply, as far as I know, through university. You need to submit an application. You need to get some reference. If you need to apply for example, fellowship program, you need, again, to have references, apply. There is some online application. And then it depends also for a staff position. In that case, you have an application, but also an interview. You don't have an interview for a summer student or fellowship, but you have an interview for the permanent position or something. So it depends a little bit on the position. But I mean, if you go on a CERN site, you find all the details with all the procedure and all the information.
So thank you for your nice presentation and wonderful discussion session. So I would like to say thanks on the behalf of the Department of Physics, Pabna, University of Science and Technology. So thanks, Virginia, for joining with us and helping us. It's a very good virtual conference and organized jointly by CERN and Department of Physics, Pabna University of Science and Technology. We would like to say thanks, CERN, for selecting our department for their virtual conference host. So thanks again, both of you, and hopefully we will arrange another virtual conference with CERN. So thanks again. Bye for today.
Okay. Well, just one thing. What do you want to do for the slide? Shall I upload them on the?
You can send me. Then I can send our student. So,
okay, because it's 80 megabytes, so I'm not sure. Okay, I'll try to share you. Yeah. Okay. Otherwise, I can upload. The visit service send you.
You can upload there also.
Okay. Then you can download and share with the student. Okay.
Right.
It's fine.
Thank you for the